Welcome to Sigma Solver, guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So, without any further ado, let's get started. Today we are going to discuss about Bresenham's algorithm and how we can use it to basically draw a straight line. So, let's read the question first. What is the theme behind Bresenham's method? Write down the procedure as well as the Bresenham's algorithm to generate a line segment between two given points, showing the working of the algorithm by drawing a line from 2,3 to 8,7 by using the algorithm. Now, the principles that we will see here are applicable to all other forms of Bresenham's algorithm applied at, you can say, for polygons, ellipses, circles and elsewhere, right? So the basic concept stays the same. Introduction. When we draw a line on paper, it looks continuous, right? But when we try to draw a line on computer screen, we face some challenges. So the challenge being the screen is made of pixels, right, which are discrete in nature, and a line must pass through the pixel centers or between them. Okay, so either the line would pass something like this, right, where the center is available, or it should pass somewhere from here, right, from the exact middle of the two pixels, right. It cannot pass, you can say, if we zoom in on a more greater level, it cannot pass somewhere from here, right. Either it will be from the center itself or the intersection or the other center. That's it. So that is kind of the problem here. So the problem is, how do we choose which pixel best represents a straight line between the two given points? Okay. So in order to do that, we'll have the algorithm. This is a fast and efficient way to generate a straight line between two points in a grid scenario, right? So pixel based display. Now this is obviously an example, but the same idea or intuition can be applied elsewhere as well. Even in uh, real world scenarios where we have a discrete sort of coordinates and we want to frame a line in that. This was developed by Jack Bresenham in 1962, just a trivia. The algorithm uses only integer arithmetic, right? This is something that is quite new, I'll say, because the earlier method which we have seen, the DDA algorithm, I'll put a link in the I button here, didn't contain the integer arithmetic, right, which caused a bit of slowness in that one. So this will obviously be much faster than that. So there will only be addition, subtraction and bit shifting, right? No floating point operations. This made it ideal for early computer graphics hardware back in those days, and it is still in use with embedded systems, CAD and raster graphics, right? So these are some of the very popular kind of topics right now. So now we'll elaborate on them, like where it is used these days. So as said, Bresenham is being used in computer graphics for drawing lines, circles and polygons. It is used in embedded systems for plotting on dot matrix printers, right? Next, it is used in game development for efficient rendering of the wireframes. Then it is used in robotics and pathfinding, basically what I just said, as in grid based path visualization traversal. One example of game development would be something like Pokemon Go, right? That is a very good example of this one. Okay. Next is the problem. We want to draw a line segment between two given points x0, y0 and x1, y1. So in this question we have x0, y0 as 2, 3 and x1, y1 as 8, 7, right? So the slope is simply y1 minus y0 by x1 minus x0, which comes out to be 2 by 3, right? So the slope is less than 1, meaning the line is gentle, right? We move along x and decide y, right? So since it is less than 1, we'll have to basically move along the one which has greater command over the line direction, which is x, and then y. So the idea behind Bresenham's algorithm is something like this. We move step by step in the x direction, right? For this example, for each x, we need to decide, should we keep y the same, right? That is the first question we'll calculate on, whether we keep the y same or not, or should we increment y by 1 in order to stay close to the actual line, right? We are obviously approximating here as well, but the idea is to keep the line even in discrete scenarios as close to the actual line. To decide this, we need a decision parameter, which we will see. So the algorithm for slope when 0 is less than m is less than 1 is something like this. Input, we get the two input endpoints, we compute dx, which is x1 minus x0, and dy, which is y1 minus y0. Then we see the initial decision parameter, which is p0 equals 2 dy minus dx. We start from the initial point x0, y0, and we then go into a loop. For each step until x1, means until the last point is reached, we see if p is less than 0, right? If p is less than 0, then the next point would be x plus 1 comma y, right? And the update logic for p would be p plus 2 dy. Okay, this is something that has a long, you can say, derivation. Do let me know in the comments down below if you want to see the derivation for that, and we can tackle that in some other video. Then this is the else part, when p is either equal to 0 or greater than 0. Then the next point would be x plus 1 comma y plus 1, and the update logic for p is also changing, which is p plus 2 dy minus 2 dx. So you might ask, like, we would have other scenarios as well with the changing sign and behavior of m. So those cases have been discussed below. Okay, so now we'll see the worked example of that. So from line point 2 comma 3 to 8 comma 7, we'll see initialization dx equal 8 minus 2, which is 6, and dy equals 7 minus 3, which is 4, right? So we calculate p0, which is 2 dy minus dx, and it comes out to be 2, right? So for the second case, this one, which is the else part, starting point is 2 comma 3. For iterations, we see for the first step, right, the xy plotted would be the same point, decision parameter is 2, p greater than equal to 0, so choose 3 comma 4, right, x plus 1 y plus 1, and calculate p accordingly, right? So that is the first step. Next, we come down with the calculated values of p, which is this one, right? We'll see that now we have the xy plotted as 3 comma 4. Then again we'll see the same thing, which is we take p less than 0, we choose this time x plus 1 comma y, right? So 4 comma 4, update p accordingly, and so on. We just simply follow this rule, right? There are two rules only, which I just told you, and it is important to like keep a track of which p are we taking, right? Stuff like that, and which point are we trying to get. So as you see, the point that we choose here comes down to the first column or the plotted column in the next row, and likewise. So this will continue to do up till the point when we actually reach the point, right, which is 8 comma 7, right? So this doesn't depend upon like the number of steps, right? That is something we've seen earlier, but this intrinsically means that the time up till when you will reach the final point, you need to continue, right? So the final points are 2 comma 3, 3 comma 4, 4 comma 4, and so on, right? And the inference that we can draw from this one is the algorithm efficiently chooses the closest pixel to the actual line, which we've seen. It avoids the floating point calculations, right? It produces visually straight lines, which is something that we can see if we plot these in the actual grid, right? Then comes like the modifications that we can exercise on this particular methodology. So circle drawing algorithm is also there, which is kind of the extension of this algorithm. Then there is ellipse drawing algorithm as well for modified version of ellipses. So likewise in these two scenarios, these are quite similar to each other. This one, the generation of all slopes for greater than 1 or negative slopes, the algorithm is adapted by swapping x and y, which we will see though below. And then there is like the 3D Bresenham algorithm, right? So this is primarily used for voxel based rendering and robotics, right? Something related to ray tracing as well, which is a very hot topic these days. So in game development specifically, there also we've seen Bresenham algorithm being applied, right? So next comes kind of the future scope or the study which can be done with respect to Bresenham algorithm is anti-aliased line drawing, Wu's algorithm, right? How to smoothen the jagged edges, right? The GPU optimization part, which is extending Bresenham algorithm for parallel processing, right? For modern graphic cards and how we can simulate parallel processing via Bresenham algorithm. Then there is pathfinding and grid navigations, right? So similar to what we just spoke about, it's like the drawing methods that we have for discrete line and movement planning, right? So now we will do the last part, which is kind of the generalization of Bresenham's algorithm for different slopes. So we'll see the line equation is between 2 points x0 y0 and x1 y1, right? We always compute two things, dx, which is the mod of x1 minus x0, and dy, which is the mod of y1 minus y0, right? We also define the step direction in both axes. So we'll mark its sign as sx equals sine of x1 minus x0 and sy equals sine of y1 minus y0. We'll now segregate this into separate cases, right? So the first one we have already seen, which is the gentle positive slope with 0 less than m less than 1. We iterate over x, right? The decision parameter is p equal 2 dy minus dx, and the update rules are like if p is less than 0, then x comma y plus 1, p equal p plus 2 dx, else x plus 1 y plus 1, and p plus 2 dy minus 2 dx is the update rule, right? Now we come to the second case, which is m greater than 1, right? Steep positive slope. So y changes faster than x, so it's just the swap of that. We iterate over y instead of x, okay, and then the initial parameter would be 2 dx minus dy. Update rules: if p is less than 0, right, then x comma y plus 1 and p plus 2 dx, else x plus 1 comma y plus 1, p plus 2 dx minus 2 dy. Now we come to case 3, which is the other one, which is negative gentle slope, minus 1 is less than m, which is less than 0. Again we iterate over x, okay, and the initial parameter is p equal to dy minus dx, but we know that dy equals y1 minus y0 mod. So the update rules will be similar as in we had previously: p less than 0, x plus 1 comma y, p plus 2 dy, else x plus 1 comma y plus 1, where p equals p plus 2 dy minus 2 dx, right? Here we saw that we decrement y when crossing the decision boundary for the line, right? Next is case 4, which is when m is less than minus 1, which is steep negative slope, right? We iterate over y again. This time the initial parameter would be 2 dx minus dy, right? The update rules in this one would be p less than 0 equals x comma y plus 1 and p equal p plus 2 dx, else x plus 1 comma y minus 1, where p equals p plus 2 dx minus 2 dy, right? So again, that was the 4 cases. We have horizontal and vertical lines as well, but that is something quite obvious, right? Those are fine. Then there is like the Bresenham pseudocode for all these slopes combined. So that is something which we have in the Sigma Solver community. Along with that, many other questions and the modified versions of Bresenham algorithm, right? And other things we've discussed slightly in this video are covered in detail inside the community. So if you are interested in any of those, I'll suggest you to join the community by clicking the link in the description below. If you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.